Hello, and welcome to our example of using Fourier coefficients and Fourier series to solve a partial differential equation that, for a change, is not a heat equation type problem. We are going to solve the periodic transport equation ux plus ut equals 0 on the domain x is between minus pi and t is a real number, with the additional requirement that u of minus pi t equals u of pi t for all times t. So the PDE part, ux plus ut equals 0, is just a familiar transport equation, and we know what the general solution to that should look like. But now we are restricting ourselves to x between minus pi, and we want this periodicity in the x variable in our solution u. So as usual, we'll assume we have a solution to this problem, and we'll find the Fourier coefficients of u. That is, we'll work backward, and then once we have the Fourier coefficients for u and a possible formula for u, we'll see if that formula makes sense and is continuous and differentiable. So what are these Fourier coefficients of u? Well, u now depends on two variables, x and t. How should we evaluate the Fourier coefficients? We'll take the coefficients in the x variable. This is the space variable. I mean, t is time, so x probably should be space, and so often I will call x the space or spatial variable. And so we find u hat of kt is 1 over 2 pi integral minus pi to pi u of xt e to the minus ikx dx. So look at that integral for a moment. The variable of integration is x. K is the integer that appears in the Fourier coefficient, and now t is just coming along for the ride as a parameter. So the Fourier coefficients depend on integers k and times t now. So if we look at the transport equation on the Fourier side, what are the Fourier coefficients of that equation? We get 0 is ux hat of kt plus ut hat of kt, because Fourier coefficients in one or two variables are linear. Now this first derivative we know how to handle. This is an x derivative for u, and I'm taking the Fourier transform in x. So I get ik u hat of kt plus ut hat of kt. So the first term is familiar thanks to our previous video and how we know how Fourier coefficients and derivatives play. But what about this time derivative, ut hat? I'm differentiating with respect to time in u, but I was taking the Fourier coefficient with respect to space. This is the kth Fourier coefficient of ut at time t. Is there a way for us to figure out a better formula for ut hat? Because otherwise, our Fourier side version of the transport equation isn't that useful right now. Let's just calculate what ut hat at kt is. This is 1 over 2 pi, integral minus pi to pi, ut of xt, e to the minus ikx dx. So I've just stuck now this ut function in the integrand where before I had u. Can I do anything to this integral? Note carefully what's happening inside the integral. I'm differentiating u with respect to t, but I'm integrating with respect to x. So the variable for the derivative and the variable for the integral are different. This isn't a fundamental theorem of calculus thing where the integral and the derivative will cancel each other out. Instead, we need something new called the Leibniz rule for differentiating under the integral. Here is a hand-wavy explanation of what happens so we can get on with our PDE problem, and at the end of the video we'll come back to the rule in more detail. We want to pass the derivative outside the integral. Here's the bad, but also, I think, good reasoning, though it's mostly bad. Integrals are infinite sums. Derivatives and sums commute. So, in the best of all possible worlds, I should be able to pass this t derivative outside the integral. And so, ut hat of kt is this integral 1 over 2 pi, integral minus pi to pi, ut of xt, e to the minus ikx. And if I were able to pass that t derivative outside the integral, this would become the t derivative of the quantity 1 over 2 pi, integral minus pi to pi, u of xt, e to the minus ikx dx. Now look at what's inside the square brackets here. This is an integral taken in the variable x. So my dummy variable of integration is x. I don't have to write x here. I could put w or c or theta or whatever. K is a fixed integer now. K is a parameter of this integral. T is the only thing that is moving, the time variable of u. So this whole expression in square brackets is a function of t, so I'm allowed to differentiate it with respect to t. And of course, I recognize this derivative here, what's inside the square brackets. This is just u hat of kt. So I'm differentiating u hat of kt with respect to t. And so now I've got an expression involving the Fourier coefficient of my original function u. So the transport equation on the Fourier side, as they say, fully reads 0 equals ik u hat of kt plus ut hat of kt. And now that is ik u hat of kt plus t derivative on u hat evaluated at kt. Now there are a lot of letters here, but this is in fact a first-order linear ODE. And why is that? K is now a parameter. I square root of minus 1 is just a constant. And the function here, u hat, depends on the parameter k and the moving variable t. So this is a t derivative on u hat plus a scalar multiple of u hat. We solved these back in our first week together. So how can we solve this ODE? T derivative on u hat of kt plus ik u hat of kt equals 0 for k an integer fixed. Well, I would just use the integrating factor method. I get u hat of kt is a constant c of k times e to the minus ikt, where the constant c of k can now depend on k. The important thing to realize is k is a parameter. So for every different integer k, I get a different differential equation for u hat. So each of these differential equations, when I'm writing down the final solution, I have to be able to track any constant's dependence on k. Thus I have a c of k here, not just a plain old c. So take a moment, hit pause if you need to make sure you understand how u hat of kt is c of k times e to the minus ikt. This is why we spent all that time on familiar first-order equations at the start of the course, so now we can handle them with parameters. Now that we know what u hat of kt is, we can write down a formal expression for its solution in terms of the Fourier series. U of xt is the sum from k equals minus infinity to infinity of u hat of kt times e to the ikx. And now we know what u hat of kt is. So this is the sum from k equals minus infinity to infinity, c of k e to the minus ikt e to the ikx. Or if you prefer, sum k equals minus infinity to infinity, c of k e to the ik x minus t. Again, remember, we worked backwards. We supposed that we had a solution to the transport equation that was 2 pi periodic, or defined on the interval minus pi to pi. We found the Fourier coefficients in space. We know that if the function u is sufficiently continuous and differentiable, u equals its Fourier series pointwise. That was my first equality here. And then we just chased through what all the components of the Fourier series are and arrived at the sum over all the ck's e to the ik x minus t. Now our natural question is, does this sum converge? So if we have a solution to the transport equation, then yes, the solution looks like the sum and the sum converges. But suppose I just give you this sum. How can you verify that a function defined by this sum actually does solve the transport equation? Well, the first thing you should do is make sure that this sum converges pointwise so you can talk about the function u of xt equal to this sum. And if the sum converges, is it continuous and differentiable in x and t? This is just what we asked in our last video for the ordinary differential equation solved by Fourier series, except now we have a PDE, so we have variables x and t to consider. Well, the only thing we have to choose here now, our only freedom comes in selecting these constants c of k. And that would depend more on initial data. If I had some time t equals 0 initial condition in my PDE from the beginning. That might tell us more about what C of k is. One thing we can guarantee is that if the synchronous sum k equals minus infinity to infinity of modulus of ck converges, in other words, the ck sum converges absolutely, then yes, the sum for u of xt will also converge by the comparison test, because the modulus of the exponential is just 1. So if I select my ck's reasonably well so that this doubly infinite sum over the ck's converges, then yes, I get all the convergence that I want in u of xt pointwise, and from that some additional theory, which we won't do in this class, would tell me more about the continuity and differentiability of u. Now let's think about something else we know. This transport equation, ux plus ut equals 0. We could solve this lickety-split based on work we've done in previous weeks. We know the general solution is u of xt equals f of x minus t, where f is some c1 function that depends on a single variable, c. So let's suppose that I put f of c equals this sum from the previous slide, sum k equals minus infinity to infinity, c of k times e to the I k c. And I've supposed that I've selected my coefficients c of k so that the sum for f converges for all real c. If I do that, then my Fourier-derived solution, u of xt equals sum k equals minus infinity to infinity, c of k times e to the I k x minus t, just compresses as f of x minus t. In other words, if I stare carefully at our Fourier-derived solution, I can put it in a form that respects the general solution to the transport equation. This is one of the reasons I love the transport equation, because you know what the general solution is, and all these different techniques, Fourier transforms, later Fourier series, always bring you back to the same solution, so you know you've done something right with your life. Now last, as I promised, a little more on the Leibniz rule for differentiating under the integral. We've solved the transport equation with Fourier series due to that key insight of differentiating under the integral. We've talked about how the Fourier series converges. How did we, though, get to differentiate under the integral in the first place? This is Theorem 2.4.35 in the current numbering of the notes. Let me start out with intervals a to b in the reals and I. So ab for us today will be a closed bounded interval. I can be any interval. And I'll suppose I have a function f, and this is a function of two variables. So the mapping x goes to f of xt is continuous on the interval a to b for any given t and I. And I'll call this mapping sometimes f of dot t. Often when I have a function of two or more variables and I have one parameter fixed, like t, I like to put a dot to indicate that the thing that's moving is what's going into the dotted slot. So f of dot t is indicated to be a function of x with t as a parameter. And the partial derivative, ft of xt, or partial t on f at xt, this exists for all x and t. And the mapping of xt going to this partial derivative ft of xt is continuous on the product ab cross I into the complex plane. If the notion of Cartesian product gives you pause, remember this is just all ordered pairs with first entry in the interval a to b and second entry in the interval I, and I do discuss this in our appendix on set theoretic notation. So I have this function of two variables. It's continuous in the x variable, and it's differentiable in the t variable, and the t derivative is continuous jointly in both x and t. Then the mapping that sends t to the integral a to b of f of xt is continuous from the interval I into the complex plane. So look at this mapping. I have my function f of xt in the integrand. I'm integrating with respect to x. You fix a t and I integrate with respect to x over the interval a to b. I can totally do that because f is continuous in the x variable from part 1. And so I've assigned a mapping that sends a number t to this t-dependent integral. And it's also differentiable. And the derivative of the integral from a to b of f of xt is the integral from a to b of ft of xt. In other words, I can pass the derivative through the integral. And back in our transport equation problem, Remember, we were working backwards. We assumed we had a solution u of xt to the transport equation. Implicit in that assumption is that u is continuously differentiable with respect to x and t. So that function u satisfied parts 1 and 2 of these hypotheses. And that was why I was able to pass the derivative under the integral for the Fourier coefficients.